Okay, there's 1 minute left. We will start in about 1 minute. Okay, it's 2 p.m. Let's get started. Hello and welcome to today's webinar, the Fraunhofer IPMS technology webinar. The topic is MEMS-based micropositioning platforms. This webinar will be held by my colleague, Dr. Christine Ruffert. A few details about her. She was born in 1978 and completed her PhD at the University of Hannover in the field of engineering science in 2007. She got her habilitation at the University in Braunschweig in 2017 in microfluidics. And Ms. Ruffert has worked ever since in several positions as project engineer and scientist in this area, and joined our institute, the Fraunhofer IPMS, in 2019 as a group leader for microactuators and sensor systems in Cottbus. She also works at the chair of micro and nano systems at the Brandenburg University of Technology. Okay, before we start, if you have questions during the webinar, please use the taskbar on your right and type them in. We will address these questions after the webinar. And you will receive a follow-up email tomorrow, including the slides and all the contact information. And you can re-watch this webinar at any time. So, Christine, are you ready?
Yeah, I'm ready.
Take it from here.
Thank you, Peter, for the nice introduction. So also a warm welcome from my side. Welcome at the Fraunhofer IPMS, at least virtual. Yeah, the Institute for Photonic Microsystems. Yeah, I don't have to introduce myself anymore. So let's get started. And yeah, we just step into what will expect you within the next maybe 25 minutes. Yeah, we have developed a new kind of an electrostatic drive, which we call nanoscopic electrostatic drive, or abbreviated NED. Yeah, it's an own development from IPMS, and it's also, of course, a patent and so on. And so that's why you don't have to be astonished why you never heard of it before. So at least I expect it to be. And then I will introduce the basic working principle, yeah, the principle of the drive, of the NED drive. And then I will introduce you some micropositioning systems. We have an XY table, yeah, which is based on a 1D drive, and you will also get to know the 2D table. And then we will learn from another drive, an inchworm drive, and this is a 1D system, but another approach, also based on the same driving principles. I will present you some advantages and also applications, and I will close with a summary and an outlook. And then I hope you will have some specific questions on the systems. So yeah, welcome at the branch Integrated Silicon Systems in Cottbus. Yeah, our Manda Institute is located in Dresden. Yeah, my colleague is sitting in Dresden. And this branch was opened about 5 years ago, yeah, 2018 actually, so 4 or 5 years. And yeah, this is a view in our lab. Yeah, I'm sitting at the microscope here. And what are we doing in Cottbus? Yeah, because as I said, Dresden is our mother institute. We have the clean room in Dresden. The fabrication is done in Dresden, but a lot of things happen also in Cottbus. Yeah, so our focus is on characterization, not the fabrication, and in many fields of application. So just to name a few, yeah, we are also working on microfluidics here. Microlinear positioning is our topic today. We are also working on terahertz components, RF components in the optical area. I mean, we are the Institute of Photonic Microsystems, so it's not astonishing that I mentioned optical systems. And we have a field or a group working on speakers, loudspeakers, ultrasonic systems. And maybe allow me to mention one thing. We had a spin-off about 2 years ago, which was called Arioso Systems first. Yeah, and after 1.5 years, it was how to say, bought. Yeah, it was included into Bosch Microtech. So our spin-off is now Bosch Microtech, and we are really proud of it, and that's why I mentioned. And this is our business field, MEMS loudspeaker, and this has the same driving principle as I introduced today. So it's the same NED system as a basic drive, basic component of those loudspeakers. Yeah. So I hope you're curious to follow my talk. Let's start with some physical basics. Yeah, my colleague, I think he mentioned I'm a physicist, and I like to give you a basic lecture, but don't be afraid, just some basics on physics. So maybe you remember from school, a capacitor, yeah, two plate electrodes facing each other, and then we apply a voltage, and the two plates try to come together. Yeah, so the distance is lowered, and we have a certain limit of stability. Yeah, and when the distance becomes lower, yeah, we will follow this curve. So we start the voltage, we apply a voltage, and then the gap becomes smaller and smaller up to a certain limit, yeah, which is also mentioned or noted here. And then the system will collapse. This means the two electrodes will come into contact. Yeah, but this is something we don't want, because then they attach electrostatically and we cannot do anything more. The system is dead. Yeah, we cannot move anything more. And in school, yeah, the teacher tried to separate the two electrodes manually, but we cannot do, because we're in the microsystem range. Yeah, so our electrode gap is maybe only 1 micron or maybe a few hundred of nanometers, so we cannot do anything manually. Yeah, we have to prevent that the two electrodes come into contact, which is also called pull-in. Yeah, and yeah, maybe I just go to the next slide. So what we did, we shaped those electrodes in a certain shape we call dome shape, because yeah, when you see this dome structure on the left, yeah, it looks like a dome door or window or whatever. And imagine, yeah, we shape our electrodes like this, and now we apply a voltage. So the upper and the lower electrode will still try to attract each other and come into contact, but they can't, because of the topology and because of the surface structure. Yeah, and when I consider this as an elementary cell, what will happen when I apply a voltage? The upper electrode and the bottom electrode, which is not shown here, but we have it in mind, and you will see on the next slide more clearly. Yeah, they will attract each other, and this elementary cell will, yeah, the side walls will bend, and it will D-shape, let's say. Yeah, and imagine I take a row of those elementary cells, I put them in a row like a cantilever. Yeah, then I apply a voltage. The electrodes try to attract each other. The system bends, the sidewall bend, and then also the cantilever will bend. Yeah, and I'll show you on the next slide how we make use of this as a drive, as an electrostatic drive. So we see the bottom electrode here in gray. Yeah, it's made of silicon. The upper electrode is green. Yeah, previously it was made of titan aluminate, but now it's also silicon. Yeah, but we can distinguish better when it's not the same color. So we have two electrodes, green and gray. They are separated by a spacer made of alumina, yeah, which is the blue one here, to avoid an electrical shortcut, of course. Now I apply a voltage. Yeah, and the two electrodes, the top and the bottom electrodes, try to get into contact. Yeah, they try to do the pull-in, but they are not allowed to. So what happens? The cantilever will bend. Yeah, I can do the same thing the other way around when I put the spacers not in the valleys here, but on the tips. Yeah, and then the cantilever will bend to the top. Yeah, and this approach has a lot of advantages. I can realize high deflections without pull-in. Of course, at some point I will come into a mechanical contact, but this takes really a large deflection range. Yeah. So in the basic paper we mentioned 5,000% of deflection, which means travel range related to the electrode gap. Yeah. So let's say 1 micron gap means 5 millimeter deflection. Yeah, this is really, really high. So our, let's say, unique selling point is the large deflection. And yeah, we have the stacking advantage and the scaling advantage, so we can make the cantilever as long as the wafer allows. Yeah, currently we are using 200 millimeter wafers. Yeah, so if you want a cantilever like this, it's in principle possible. And we can stack the system also in parallel. Yeah, so I will show you in the next slide. We can do it in plane and out of plane. Yeah, just to explain why I say in parallel. And the system has a low power consumption, only a few milliwatt, and it's also CMOS and ROHS compatible. This means we have We don't have any restrictions regarding hazard substances, as this expression says, like some piezo systems have, so you still have many lead alloys, and there's, I mean, silicon, alumina, will never be forbidden, hopefully, so we don't have to be afraid of this. So as I mentioned, we have two basic principles. We have the lateral movement and the vertical movement. We call it L-net and V-net, for lateral and vertical net. And just maybe briefly, for those who are interested in the fabrication, I saw someone from Infineon's also there. So the electrode gap in case of the L-net is made by deep rective ion etching as basic technology, also called Bosch process, of course. I think you already knew when you saw the structures. And the vertical net is made, or we have two possibilities for the vertical net. One is making use of a sacrificial layer. So we have a one wafer and use a sacrificial layer here to pattern the gap. And the other approach is based on a two wafer approach. So let me summarize the basic of our actuator, and then I will present you our micropositioning systems. So we have the basic cantilever, and we can deflect it out of plane and in plane. And just to remind you, it is based on the deflection of the side walls of this elementary cells, and here I listed the basic advantages again. So now let's have a look what we did with those actuators with this basic principle. So on top you see a state without deflection, without voltage, it's the basic state, and you see a lot of net beams here, so every white, let's say rainbow, so we call it also rainbow actuator, is one of those NED systems. So we have many in a row and many in parallel. So now we apply a voltage, and what you see when we apply a voltage is shown here in the picture on the left, on the bottom. It's opened, it opens like a rainbow really. And in this case we applied a voltage of 120 volts, and deflection is about 0.5 millimeter. And you see we have no hysteresis. This is the way up and the way down. Open and close the system, and you see we have a fine tip here. And we think maybe with this tip we can manipulate cells, we can even electrostatically attach cells. You can think of something to grip a fiber or whatever. So we can something hold on a position or manipulate something with electrostatic forces. So this is our 1D system, and I promised I will also introduce an XY table. This is on the next slide. So here you see our XY table, and you see many of the NED actuators everywhere here, and we see the X component on the left and on the right, and the Y component in the center. It's a movable table. And maybe I show you the animation first. I think I have to skip this presentation because otherwise you won't see the animation. And I started, and maybe Peter, give me a feedback if it's seen. Yeah. Perfect. I will just stop because it's very fast. So what you see here is the animation of the XY table, and the green part here are the actuators, the NED or nanoscopic electrostatic drive. And it's a small table you can move. In this case we move our logo, but you can also move cells or micro optical components maybe when they're not so heavy. And the system moves to the left, to the bottom, to the right, and to the top. And I will start it in a second. Just one other remark. You also see those purple colored structures here. They are for the positioning measurement. So we have capacitive finger structures, which go in and out, and by the capacitance or by the change of the capacitance we measure the position and are about to realize a closed loop control and enhance the resolution even still beyond 1 micron, which we actually have as a resolution. So I started again, and you see how the table moves. It moves to the left and to the bottom. And you also see the fingers moving, and to the top. So that's the animation. And I will immediately start also a real video because the system has already been fabricated. Now you see the inner part of the XY table. which means the Y component, and the system is moving. You see how the net actuators or the rainbow actuators, they open, yeah, and close again. Just to give you, and you see also the capacitive finger structures. Maybe I started again, it's very fast. Yeah, so you can really see what happens. So the bottom part opens, the upper part closes, of course, yeah. And the system is moving up and down again. You see the scale, yeah, so this is about 1 millimeter. Okay, now you saw or learned from the XY table. Maybe I start the real presentation again. Now you should see the full scale. Now I have to change. This is a bit strange here, but okay, we will handle it. And so you see the operation voltage. Yeah, it's up to 200 volts. It depends on the deflection you want or you need. Travel range in this case, yeah, this is our prototype. The travel range is in this case about 0.5 millimeter, so 500 micron, but it can even do more. So as I said, it's a prototype, but it's not the end of what can be realized. So if you need, let's say, maybe 2 millimeter, we can design a respective system. Yeah. And the maximum force in this case is about 1 millinewton. So as I said, we cannot move heavy components. Yeah, only light components, maybe an optical fiber or so. And the motion resolution is already 1 micron. And we recently, 2 weeks ago, we recently achieved a resolution of 150 nanometer. Yeah. Here's the full system, the fabricated system. Yeah, it's made of silicon, as I said in the beginning, and the chip size here, the outer part, the footprint is about 8 millimeter times 8 millimeter. Yeah, and you see the Y component in the center, which is able to move, and also the capacitive sensing structures. Yeah, so this is our table, and we have a demonstrator here also in our library from the university in Cottbus. So when you're in Cottbus one day, you're warmly invited to visit our library and see our demonstrator running. It's really nice to see. So what we did here is we put the silicon chip with the actuation part on a PCB, of course, yeah, to get the voltage in. And we printed a small pin here. Yeah, the height is 3 millimeter. And we took a wheel from a clock, from a wristwatch. And this is the whole setup. And what happens, I will show you in a video. What happens, the pin is moving to the left and to the right, and it's turning the wheel, yeah, from the wristwatch. And it's really tricky to assembly, because when you put this part in the center between two teeth, you will turn the wheel to the left and to the right. So you have to do it this way, that it always turns in one direction. Yeah, now I go out of the presentation again. I show you the video, which I hope you will like. Yeah, so this is the chip. And now you see how the actuators are working. They are working really hard, and yeah, moving the pin. And as you see, the pin is moving the wheel. Yeah, as I said, footprint is 8 millimeter times 8 millimeter. But we can do other designs. Yeah, this was just a prototype, a demonstrator to show the basic principle of the actuators. Now I have another view from the back I will share with you. Looks like this. Yeah, and we have a small out-of-plane movement, about 100 or 200 nanometer, but we can work on this if it is required. Yeah. See the soldering bumps here, they are really large compared to the system. Yeah, and that's what it looks like. Okay, I will now close this and present the second system to you. I said I will present the 1D system, and then the 2D system, the XY table, and then the inchworm drive. And now I think we're, yeah, it's fine from time, I hope. So the inchworm is working as follows. We have two electrostatic blocks, B1 and B2, and we have a shuttle which should be moved. So now the first block is electrostatically attached to the shuttle, and then the nets, yeah, these are also nets here, they are bending and they are moving the shuttle for one step. Then the block B2 is attached and the first block is detached so that the second block can move the shuttle the second step. So they are moving the shuttle one after the other. Yeah, and this is, I don't have to read out the text. I think you got the basic principle. This is how the complete system looks like. We have two blocks. Yeah, this was only half of the system, but it explains the basic principle. So we have one block moving and one block attaching, and I think I can tell you much and you can read, but I just showed you the video and then you will get everything how it works. I also have an animation here for you. So yeah, you see two blocks on the left, on the right side, the green part. Maybe I stop and explain and then you can see what happens. So the green part is the net actuation system. We have two cantilevers in a so-called S configuration. Yeah, so we have one cantilever and the other cantilever turned by 180 degrees so that we create an S shape as you see here. Yeah, and joined here in the center, of course. And we have two blocks left and right. We have the red shuttle in the center. And now I started again, and then you see how the two blocks attach and move the shuttle in the center. Yeah, so start, and then you see it attaches and moves, and it's a step motor, of course. Yeah, it's not a continuous system like in case of the XY table, which is moving continuously. Yeah, so this is the animation, and of course we have the system ready. Yeah, so maybe I stay in this view because I need the video on the next slide anyway. So this is the complete system. Yeah, it is 88 times 8 millimeter as well, and you see the actuation block and the shuttle in the center. And now I show you a video of the real system as well. Yeah, so you see the net blocks on the left, on the right in S configuration. You see the shuttle in the center, and now the right part is moving the shuttle. Let me stop and explain, and then you can first think and then look. Yeah. So the right part is moving and moving the shuttle upwards, and the left block here is just clamping. So the right part attaches electrically and moves for one step upwards. Then the left block is attaching, the right block is detaching, and again, so in this case, the left block is only for clamping and the right block for moving. And when it goes downwards, it's the other way around. The right block will clamp and the red block will do the real work. So maybe I just show you and you will see and understand. So, and we have the shuttle yeah, with a mechanical spring for better guide, of course, yeah, and the stabilization, and the deflection or the maximal way, of course, depends also on the mechanical properties of the spring here. Yeah, and let me check. I will now it will switch from the right to the left block. Yeah, when you see really when the left block starts working. So check in a second when it goes back. So still up, and now you see the left block is grabbing the shuttle back home. Yeah, and the right block is responsible for the electrostatic clamping. Yeah, so I hope you saw it clearly. If not, and when you start your questions in the end, I can show it again. Yeah, but I will be finished in maybe 2 or 4 slides. So let me switch and summarize. So I presented 2 systems, the XY table and the inchworm system. And in case of the XY table with a rainbow actuator, we have an analog linear motion, a continuous motion. In the case of the inchworm, we have a discrete linear motion, so stepwise. Yeah, both systems allow higher or large deflection. In both cases, we can achieve, let's say, some millimeters. Yeah, we can implement a closed loop control. This is done by capacitive sensing in both cases. And we have a long list of possible applications. Maybe I switch to the next 2 slides because I have an extra slide for the applications. Yeah, and you can also make use of those drives for rotational or angular motion. So maybe first a summary of the advantages, and then we will have a look on the possible applications. So what are the advantages? As I initially said, we have the advantage that we can scale the system, we can stack it in inline, also in parallel. So we have the possibility for a large field of design. Yeah, and we can also create highly modular system. We have a high precision. We have low power consumption, like negligible hysteresis. I showed you in the curve, yeah, the respective curve. We have the compatibility with CMOS and the restriction of hazard substances, so there's no issue. And we can even put an anti-stiction coating so that we don't lose so much power for the drive. So what are possible applications? We think of course, positioning applications, precise positioning application, maybe focusing of lenses in smartphones, mirrors in LiDAR. By the way, our institute also fabricates or develops and fabricates mirrors for LiDAR, so 2D MEMS scanners, for those who are interested. And yeah, some probe tip positioning for SEM, AFM, and so on. Optical setups, of course, positioning, high positioning, and micro-optical systems. So we think of optical switches, connectors, waveguide positioning, brake gates, gratings. I think I don't have to read it out. Everything, you will get the slides anyway afterwards, but you see there's a wide field of possible applications, yeah, including also RF, terahertz, MEMS, RF switches, varactors, tuning components. In the area of medical instruments, we think of maybe an implementation in microendoscopes, laser scalpels, ultrasonic devices for sonography, etc., etc. And also maybe in the area of suppression of noise and vibration. Yeah, and here again, profilometers, AFM, atomic force microscopy. And finally, in microassembly systems, for example, cell manipulation, I mentioned in the beginning, yeah, for the electrostatic, let's say, clamping or storing of cells, yeah, when you want to yeah, put some or do something with the cells, and for micro tweezers and micro grippers. So there's a really manifold and wide field of possible applications. And to summarize, I introduced two positioning systems, the XY stage based on the rainbow actuator, the so-called rainbow actuators, and the inchworm drive. And I didn't show you the state-of-the-art systems because of time, but our performance is at least better, in most cases better, at least comparable when you look at current state of the art systems, and we have many advantages compared to piezo-based systems. Yeah, and what is the outlook? We will implement a closed loop control, and we will even work on the optimization of the performance of the device. And to finish my talk, we are always searching for industrial project partners and for your applications. So please come to us and tell us what are your specific applications and your needs, and we will highly appreciate to fulfill your needs. Thank you for your attention. Peter, should I stop the presentation?
No, you can leave it like that. Up to now, there are no questions asked. So if you have questions, please type them in now. In the meantime, I got a question. Can you give us more details about the specifications, for example, the maximum displacements?
Of course, Peter. I have a backup slide or two backup slides. I will show you. Sorry, they are not shown. I don't know why. Should be that's the final slide. Okay. So as I already said, it's about several millimeter we have. I have to switch the view. So this way, now you should see it in the right way. Yeah, so the XY table currently moves about 500 micron, but it's another design would even allow more, yeah, maybe some millimeters. And in case of the inchworm, which is presented on the next slide, it's already moving some millimeters, yeah, and maybe some more specs. So one question is always the resonance frequency. So the resonance frequency is in the range of some 100 hertz up to 800 hertz, 1 kilohertz, but we are not driving the system in resonance, so it's rather a quasi-static mode. And the maximum load mass is about 10 milligram, as you can see here. A crosstalk error is less than 1%. And for those of you who are interested, let me know. I can send you, of course, the specs after the webinar. Here are the specs of the inchworm drive. So the driving voltage currently is 200 volt, but we are on the way to scale it more down, to make it also transportable. And you see the footprint and the basic dimensions. And here you have eigen frequency, a resonance frequency of about up to 10 kilohertz. And what do we have else? So system travel range of several millimeter. And maybe I have not a question from my side, but you are warmly welcome. Maybe I go back. You are warmly welcome to tell us your specific application. So when you don't have questions at this point in time, maybe you have some remarks or ideas where we can make use of our positioning system or our positioners. So it doesn't have to be now, also afterwards, because as I said, we are searching for partners, we are searching for your applications, and that's why we present our basic development here, because Fraunhofer is your development partner.
All right. Thank you very much. There are still no questions, so I think it's just time to end this webinar. Maybe you can switch to this slide. Exactly. I would just like to announce that there are 2 more webinars this year. You will also get this information in the follow-up email tomorrow. So maybe we will see each other again in our webinar series. And thank you for joining in. Thank you for your time. And again, Christine, thank you for your nice presentation. And have a nice day, and goodbye from all of us.
Goodbye.
Bye-bye.